And we have discussed method development in liquid chromatography already quite a long time. So we know quite a bit of this. So to improve the resolution, to improve the peak resolution, we have discussed three groups or three terms of this equation. We discussed already a retention term and selectivity term, but we are somewhere in the middle of this efficiency term. So the number of theoretical plates. And so the efficiency term, as we saw, it has this square root there. So square root means that all the effects that we gain, this has to be taken square root of, and this contributes not too much to the overall peak separation, but still it has its influence. So we can use it two ways. We can use the efficiency in order to improve the resolution, then we have to achieve higher plate number, or if we see that the peak resolution is good enough, then we can go by the way of reducing the number of theoretical plates and therefore making the analysis faster. So both ways are possible, or both uses. We took a starting point of 15 centimeter column with traditional 4.6 millimeter internal diameter, and very roughly we can estimate that these kind of columns with 5 micrometer particles have 10,000 theoretical plates. That's a very, very rough estimate. And flow rate and particle size have an influence to efficiency, but also the column length. Yes?
I'm sorry, like the concept of the theoretical plate is like when you buy the column. So if you're not getting a good resolution, the only way to change the number of theoretical plates is changing the column?
Well, yes and no. Well, if the chromatographic conditions are not favorable, then the number of theoretical plates is low. But if we put the question in this way, that if you buy a new column and use optimized conditions, and under optimized conditions, still the number of theoretical plates is not high enough, then we can complain to the supplier that, well, you gave me a bad column. So under optimized conditions, and optimized means, first of all, flow rate. As we know from the Van Dinter curve, flow rate has an influence on this number of theoretical plates.
But the chromatographic conditions are like something that can cause a change in the number of theoretical
yes.
plates.
Yes.
But it's just a theoretical concept, right?
Theoretical plates?
Yes.
Well, the plates itself physically do not exist. In this sense, it's a theoretical concept. But the characteristic, we can calculate it from the experimental data. It's in fact just a ratio of retention time and peak width. So,
but it's a concept. Like it doesn't exist.
Like plates inside the column do not exist. Yes.
So you can say it's just a parameter to like determine the efficiency, or like.
Yes. Yes. In this sense, yes. Do you agree? Yes? Very good. Okay, so, and as said, the Van Dinter plot has a minimum And this means that the height of theoretical plate at some flow rate is the lowest, which means that the efficiency is the highest. So height of theoretical plate and number of theoretical plates, they are inversely related to each other. So the bigger is the height, the lower is the plate number. Okay, for bigger particles, like 10 micrometer diameter particles, the height of theoretical plates, even the optimal one, is higher. For smaller one, it's lower and lower and lower, so the smaller is the particle side in the column, the higher efficiency we can expect. Now, coming to the column length, if we consider 15 centimeter column, the classical one, then if we replace it with 10 centimeter column, then all the retention times, also the dead time, will be just 33% shorter, just because the column is now 33% shorter. And resolution decreases, and now the slide says 6%. I don't remember where did I take this number. I think I didn't calculate it myself, because for some reason I wanted to calculate it today, and this 6% doesn't seem to be correct. So let's think about this. So if we take, let's say, 15 centimeter column, and say that it has 10,000 theoretical plates, as we assumed in the beginning, then what if we change it to longer column, twice as long as 15 centimeters, so 30 centimeters? How many theoretical plates will it have then? Yes, twice the same number. Yes, approximately twice the number of theoretical plates. So it will be 20,000. And now if we consider this from the peak resolution equation, the efficiency term, then efficiency-wise, it was square root of efficiency. So let's calculate how much we gain if we change to twice as long column. So twice as long means the square root of 2 times n, as we saw, which means we get the same resolution as before, and multiplied by RS as before, multiplied by square root of 2. So if this gives us RS, the resolution, then with 2 times longer column, we obtain 2 times the number of theoretical plates, and the peak resolution will be just 1.4 times higher. So 1.4, because square root of 1.4. Now let's imagine that we make the column shorter. So instead of having 15 centimeter column, let's use 10 centimeter column, which means that the column is now 0.66667. And the same way, the number of theoretical plate will be 0.667 times the number of theoretical plates. Right? This 0.666 comes from 10 divided by 15. But the column length is now smaller. And this takes us to RS square root 0.667. And if I calculated this, then I think it was something 0.82. So 0.667 square root gives us 0.82. So it's 0.82 times RS, which means it's about 18% smaller. Not 6% as the slide says, but 18% smaller than the initial one. So where did this 6 come? I'm wondering. Probably I found it somewhere in the literature, but didn't check how the number was obtained. So sorry for this. I will replace it here. It's 18%. And let's delete this. Okay. So if this 0.82 resolution, 0.2 times the initial resolution is still good, we can get the separation that we need, then we can just save time by using shorter column. We save time, we get shorter retention times, and saving time 33% is quite a lot. So 1/3 of time saved is quite a bit of time. This also means that we save eluent, so savings are quite good. And also the reverse, if we indeed the initial peak resolution is not good enough, and we see that we need better separation of peaks, then we can use 2 times longer column and can expect 1.4 times better peak separation. And this helps us, then we have achieved our goal. All right, now back to particle size. Let's imagine that we have 2 columns of the same length, but a different particle size. So nowadays, particle sizes below 2 micrometer in diameter are used. So sub 2 micrometer stationary phase particle size. And now if we compare it to the classical 5 micrometer particle size, then what we achieve with smaller ones is that the number of theoretical plates will be 3 times higher. Then the resolution will be 1.7 times better, just square root of 3. Then if we check back to the Van Ginter curve, then in principle we can increase the flow rate above the optimal, and we won't lose much of the efficiency. So we can make the chromatography faster practically without loss of efficiency. So we can perform the analysis faster. Well, there is also a price for this. The price is high pressure. So compared to 5 micrometer particles, the pressure required to pump eluent through the stationary phase is much higher. And this means that we need more efficient pumps, also more expensive ones. And the maintenance will be critical in those instruments. Okay, just for a moment, I will jump back to this Van Ginter curve to show that higher flow rates do not decrease the efficiency as much. So for 1.9 micrometer particles, even if we go to higher flow rates, then the efficiency more or less remains the same. But in case of 5 micrometer particles, the efficiency would be quite dramatically worse after increasing the flow rate above the optimal one. Okay, just some numbers. If we take our this example column, 15 centimeter long, particle size 5 micrometers, and in this source, in this literature source, they chose 12,000 theoretical plates. Well, in some experimental conditions, quite reasonable. Then also in that example, there were two peaks. The separation was 2.0 and pressure was 2000 psi, and retention time for this analysis was 15 minutes. Now, if we compare it to 15 centimeter column, also 15 centimeter. Yeah, but particle size is now 3 micrometers, so smaller particles. Then indeed we have more theoretical plates, as I mentioned. Peak separation, peak resolution is better, so 2.2 instead of 2. The retention time is still the same. This is determined by the column length, but we see that pressure is more than 2 times higher. So much higher pressures are required for this kind of analysis. Now, if our aim is to get something similar to this 15 centimeter column, so that the resolution would be similar and the peak resolution would be similar, then we could use 5 centimeter column. So instead of 15 centimeter, now 5 centimeter. The stationary phase particle size 1.7 micrometers. And now we see that the number of theoretical plates is pretty much the same. Also, the peak resolution is quite the same. Well, the pressure is still high, but if our instrumentation can tolerate this, then that's fine. And as a result, we will save we save 3 times the time. So instead of 15 minutes, now it's 5 minutes. So quite big savings in terms of time. Well, yeah. Here in this upper table also some dependencies are shown, so that the peak resolution depends on the particle size, just 1 divided the particle size and square root of the particle size. So, and number of theoretical plates is similar, just without this square root, quite understandably. And pressure is 1 divided by particle size squared. So this helps to estimate what the pressure would be in the column if we use column with a smaller particle size. Okay, so the point from here, if we decide to use column with smaller particle size, then we can increase the efficiency and accordingly the peak resolution improves. But this also brings about the higher back pressure. So we have to optimize back pressure, resolution, and in that case we can save time by using smaller particle and shorter columns. Okay, now once again, column parameters to improve efficiency. So if column is well packed, flow rate is optimal, packing particles are small, mobile phase viscosity is low, and or temperature is high. Well, those both play the same way. And analyte molecules are small. Now, up to this point, what do those points remind you? Sorry? Just a hint. Hint is here. Those all come. Yes. They all come from this Van Dinter equation. So as we already discussed in our first topic, those all are from the Van Dinter equation. So well-packed flow rate is optimal, small particle size. They all contribute to the increased efficiency. Now, dead volume is minimal. This is not visible in the Van Dinter equation, but this is something that is necessary to keep the peaks narrow. We can imagine that if the peaks obtained in the column are narrow, but they enter in a tube between the column. So column is here with its packing and everything, so that element flows like this. And after the column, detector should be used. If this distance is short, case number 1, and then case number 2, another LC system where this distance is for some reason long. I don't know why somebody decided to install so long tube between the column and detector. So how do you think, which is the better way? Upper one. Why? Here, resolution will be better. Why? Wider. Because in a long tube, when the liquid flows, it mixes and the peaks get broader. So this after column, this dead volume after column, this should be minimal to avoid peaks spreading. If the dead volume after the column is too long, then the peaks spread and all this superb resolution or efficiency that we obtain, this is just lost. Okay, and then finally this column is long. Well, this is additional feature. As we saw, this doesn't stem directly from the 1D inter-equation. It's a separate thing, but very important thing, and we must also consider this. So the longer the column, the more theoretical plates we have, and this improves the efficiency. Okay, and this is just a reminder that we already passed this 1D inter-equation. What we haven't discussed much is the effect of temperature, and we see that higher temperature, higher than usual, then affects the 1D interplot, and we see that at 25 degrees, the 1D interplot has quite steep rise after the optimal flow rate. But if we increase the temperature, then the curves become more flat. And we see that if we would run our chromatography at 150 degrees, then the optimal flow rate is at higher flow rate, higher flow rate is optimal, and we could use flow rates which are far from optimal without losing much of the efficiency. Do you see any problems in this? Is 150 degrees okay for you? No? Why? It's not practical. Boiling points. Well, yes, boiling points is a problem, but how could they then provide those chromatograms? There still are chromatograms, and indeed water and acetonitrile were used, and still 150 degrees. So water boils at 100, as everybody knows. So did they perform it using steam? No, it was still liquid phase. Remember the pressure. There is high pressure in the system. So at higher pressures, the solvent still remained liquid, perfectly liquid, and at high pressures, this is possible. No, it wasn't gas chromatography or vapor chromatography. No, because of high pressure, the solvent still remained liquid, and it's possible to carry out those analyses. But you are right that the question is whether the analytes are stable or maybe not. Indeed, it works with thermally stable analytes, and not with those one which would degrade over time or with higher temperatures. But I would say about 7 years ago, yes, I think it was approximately 7 years ago, Agilent company started to promote this high temperature liquid chromatography. They sold HPLC systems which were able to use those high temperatures, 100, 120, and perhaps even 150 degrees. And they did quite a lot of research in this direction, but it didn't become popular. So they don't provide those systems anymore. But anyway, at least theoretically, it's interesting. that we can increase temperature above 100 degrees, or in fact, methanol boils somewhere around 60 degrees, so it's even more surprising here. And the improvements from Agilent's materials can be shown here. So at 40 degrees, which is relatively common in liquid chromatography, the peaks are relatively broad. Retention times extend to perhaps 7 minutes. And there are several peaks overlapping. At 70 degrees, shorter retention times are obtained. Peaks are narrower and higher also. And at 100 degrees, the separation was obtained, and peaks are narrow and separated and in short time. Sorry? Peak areas, difficult to say whether it is similar or not. They seem to increase. Well, theoretically, the areas should be the same, yes. But yeah, this information was not given there. Okay, now one of the advantages of using high temperature liquid chromatography is pressure. So at higher temperatures, the liquids are less viscous, and therefore it takes less effort to pump them through the stationary phase. And we see that at 25 degrees, if the flow rate would be, let's say, 2 milliliters per minute, then the pressure on the column would be about 200 bars. In case of column temperature 150 degrees, we could use flow rate 7 milliliters per minute, and then the pressure in the column would be the same. So more than 3 times higher flow rate, and pressure remains the same. So this would be the way to increase productivity in the lab. But as I already mentioned, it's didn't gain much of popularity and is not offered, at least to my knowledge, is not offered anymore. There is one more drawback of this high temperature systems. Imagine that we have a leak in the system. So somewhere between the joining of tubes to column and column to detector, there is a leak. If the temperature is 25 degrees, then we see that liquid drops out from this joint. But at 150 degrees, it just instantly evaporates, and we have no idea that there is a leak. And it's difficult to understand what's going on and why we are getting the results the way we see them. Maybe even the analyte leaks out of the column, and this can be quite troublesome. So, yeah, such a practical point also. Okay, when this high temperature chromatography was still popular, then there was also a note that those systems should be so-called thermally equilibrated. So the lower one is thermally mismatched or not equilibrated. It means that we pump from the room temperature pump, we pump through the tube, and then it enters the column, and only the column has the temperature 150 degrees. what happens is that in some parts of the column, the temperature is higher, and in other parts, it's lower. And the result would be different proportioning of the analyte between stationary and mobile phase, and therefore the peaks will be broad. In order to get the most out of this high temperature separation, then the eluent entering the column must have exactly the same temperature as the column. So the eluent must be fully at 150 degrees in this example, and only then the narrow peaks are obtained. So this was the last slide about method development. Any questions or remarks?
If those are not longer popular, what is the normal temperature of the HPLC work?
Yeah, very good question. Room temperature plus a bit. And why do I state it like this? Because imagine that we perform the separation at room temperature. Then, depending on country, perhaps in summer the room is warmer, in winter it's colder. It may be reversed sometimes, but then there are seasonal variations. So to maintain the constant temperature, we could decide that, okay, let's all use 25 degrees. At 25 degrees, sometimes in summer, the temperatures are higher. Okay, let's cool it then. But cooling is quite difficult. Technically, it's difficult to cool things down. Therefore, it's easier to maintain higher temperature of the column, usually 30 degrees. It's quite common to have column at 30 degrees. Normally in the laboratory, we never have temperatures which exceed 30 degrees. So it's easy to keep 30 degrees in winter, in summer, all the time. Plus, at higher temperatures, the viscosity of solvents is lower. So this also is the factor for higher temperature, higher than room temperature. So a bit higher than room temperature is the most common. I would say 30 or 40 degrees and not higher.
We need that constant temperature in order to have comparable results.
Yes, the temperature should be constant. Now, the effective temperature on separation is relatively small. So do we have 30 or 35 degrees? This doesn't play much of the role. But, well, if we can easily control the temperature, then it's better to put it at 30 or 35 and keep it. So it's easy to accomplish.
So, like, having a constant temperature is not going to have a great impact in our reproduction times, but it will have an importance when we are comparing different chromatograms. Like, if I carry out these measurements, I need to have the same temperature for the next one.
Yes, absolutely. And yeah, there's one more note about temperature. What I have seen in some laboratories, including our laboratory, is that there is air conditioner. And if air conditioner is installed, of course, it regulates the room temperature. And at some intervals, it switches on and blows cold air. And then it switches off and the room temperature increases. And then again, it switches on and blows cold air. And if by chance it's blowing the cold air on the column, then this is quite an impact, and this can be visible in the chromatogram, those differences. So even if not using column thermostat, then it's a good idea to at least isolate the column from direct wind blowing on it, the air conditioner. Okay. Comment how to do the calculations having core shell particles. In the context of this method development, I think everything is the same except one factor. Let's see. I don't remember the slide number. Selectivity. No. Wait a bit. No, not here. This will be in those slides where we discuss gradient dilution. Yes, over there, this core shell or porous particles displays role. Here we are dealing with just 14, I think. No, this one. So here we're playing around just with retention factors, selectivity, and efficiency, and regardless of this pore shell or fully porous particles, it remains the same. So no difference here. Okay, so we will discuss it with gradient dilution. Okay, perhaps let's proceed to examples about this method development and this isocratic part. And let's take separation of three compounds: aniline, benzoic acid, and methyl resorcinol. Now, three compounds in a way similar or different, but let's see. And first separation was carried out on C18 column, 25 centimeters long, 4.6 millimeters internal diameter, 5 micrometers, as a couple of those analytes are acidic or basic. One is acid, one is base. And then we have to note also the pH of the mobile phase, so it's 4.6 for the aqueous phase. And organic part was, or the strong eluent component was methanol. And when we recorded the retention factors or at different eluent compositions, then this kind of lines were obtained. And we see that for aniline, well, the experimental points are, well, reasonably well on a straight line. We see that perhaps the last 2 points are inclined a bit, so, but the rest is more or less in a straight line. For 2-methylresorcinol, well, pretty much the same. So up to about 70%, it's the same. And for benzoic acid, well, maybe even up to 60%, it's fine, but after this, the points are quite scattered here. Oh yeah, this gray is still here, so not that bad, but still. Okay, so the points are more or less on a straight line. And as I said also in this initial slides, it's not strict. So yes, this is an approximation that we weight the relationship to be linear to some degree. In some range it is, but I will have one example also at the end where we see that it's not linear at all. But in this case, the relationship was linear. And we see that, as we already discussed, that we should have a look at this range where the K is suitable. Suitable means K is equal to 2. Then logarithm K is 0.3, so it's about here. You see that 20% of methanol would provide benzoic acid with big enough retention time. So if we would increase the methanol concentration, then benzoic acid would have just too short retention time. So we cannot use higher methanol concentration in the eluent. We just need to be 20 or lower of methanol. And if we look at the other end, then aniline. Aniline has logarithm K around 0.7. But if we limit the K to 10, then logarithm K1, then it's nicely within this range. So we can analyze those three compounds at 20% of methanol. Could we use even lower concentration of methanol? If we look at 10%, then we see that benzoic acid now has longer retention time, aniline also longer, and perhaps a bit higher than 1 logarithm K, which means K is higher than 10. Well, not perhaps too bad. But most importantly, we are about to lose the separation between benzoic acid and 2-methylresorcinol. So we see that those peaks probably overlap. So yeah, from this graph, it's clear that the right range is somewhere between, let's say, 15 and 20% of methanol. Then we get the separation and also the retention factors in required range. Okay. Do you notice anything strange by this? And if you compare it with the slide that we had in this theoretical part. The slide in this theoretical part stated something about the slope of those lines. Here the slope is 0.029, 0.023, something like this. how much was the slope set there? 3. Exactly. So no questions, right? Or there is a question? What could be the reason for this difference? Why we here observe 100 times smaller numbers? In fact, the reason is purely mathematical. In this theoretical slide, the percentages of organic concentration were used as fractions. So instead of 50% of organic, they used 0.5. For 60% of organic phase, they used 0.6. But in my calculation, I used 40%, 50%, 60% as numbers, so the 100 times difference. And, this is the reason. So in fact, it's pretty close to 3 if we would have used the fractions, just 0.5 and 0.6 and so on. So this is just to to be safe with those questions. Okay, now one more question. Let's imagine that we change the percent of organic modifier of percent B. We change it by 10. We change this percent by 10 from 30 to 40 or from 40 to 50. So how much does the retention change? Retention of the compound. Let's ask this question based on the example of benzoic acid, for example. Did you reach a conclusion? Let's use some different. Okay, this is percent B1, percent B2, and then this is logarithm K2 and logarithm K1. So, and the question involves slope, then we can see that logarithm k1 minus logarithm k2 divided by percent b1 minus percent b2 equals minus 0.03. Let's take approximately. Is this correct? Could be, right? Okay, and we decided that this difference is 10%, so it's 10. Just my question started from this, that what happens to retention if percentage is changed by 10? So we see that logarithm k1 minus logarithm k2 equals minus 0.03 times 10. So if we rearrange a bit, then logarithm k1 divided by k2 equals minus 0.3. Which means that k1 divided by k2 equals 10 in power of minus 0.3. How much is it? Okay. Minus, yes. So 1 divided by 2, right? 0.5. So what we see is that the retention time K1 is bigger than K2 by a factor of 2. Sorry, K1 is smaller than K1 by a factor of 2. K1 would be bigger. K1 is, yes, K1 is bigger, minus 0.
K1 should be bigger, but if it's less than 1, K1 should be smaller. So K1 is smaller than 2.
If
Yeah, there is a problem.
yes, we have problem here.
B2 minus
Yes, B1 minus B2, this should be negative, right? Mm-hmm. Yes, so negative here also, and then positive here, and then this will be 2. Yes. Messed it up with signs.
Why are we not using x2 minus x1 instead?
It doesn't matter because we have to reverse them both then. We could have also logarithm k2 minus logarithm k1 divided by percent b2 minus percent b1. Exactly the same, right? It's as if we multiply both by minus 1. Okay, but where I wanted to reach is actually here. That if we change the organic concentration by 10%, or from 40 to 50, from 50 to 60, then the retention time, or the more precisely, the retention factor changes 2 times by a factor of 2. So this is sometimes called in chromatography rule of 2. Sometimes people also say rule of 3. So it depends on exactly what this slope is. But approximately the retention factor changes by 2 or 3 in response to the change in the percentage by 10% points, to be precise. Okay. Yeah. Now this was one separation and discussion here. Then there was another separation, different column, but with 15 centimeter. Here it was 25 centimeter. Yeah, shorter column, but also C18. So column chemistry is the same. But what is important is that the strong eluent component was not methanol, but acetonitrile in this time. And what we obtained is a bit of different set of those dependencies. We see that aniline is still with the longest retention time, but methyl resorcinol and benzoic acid, at some point, they change their places, their order of retention changes, order of elution from the column. So if the organic concentration was 10%, then 2-methyl resorcinol, this line at least lies lower, and the benzoic acid has slightly longer retention time. We see that benzoic acid dot is here behind this gray one. And yeah, at higher organic phase concentrations, then the retention time order is the same as before with methanol. But it's interesting to notice that they change places at some concentration. Of course, at this concentration, 25%, then it would be impossible to separate benzoic acid and 2-methyl resorcinol. They would completely co-elute. Okay, one more example, just to show you that those dependencies are not always nicely linear, or if you guess that maybe they were not so nicely linear, then now have a look at those dependencies. And here, indeed, most of them are very far from linear. We see that for diclofenac, this yellow one, the dependency is more or less linear, but for the rest, it's very different. So this blue one stands for ciprofloxacin, is not very much affected by the organic concentration at all. And the rest has one very strange dependence on this organic concentration. So the eluent system in this case was very uncommon. Therefore, we don't go into details here, but just to mention that this kind of graphs are quite simple. And if possible, check that they are like this and use them. It's it's very good to use them. But be prepared that it can be much more complex. Yes.
In this case, 10% we can like separate
And 10%, no, because
the 2 points are like
yes, aniline and benzoic acid are overlapping.
they cannot be separated using the finite,
Not at this percentage. They can be easily separated, for example, here, but of course now the retention time is just too short.
So it's not possible.
Over here, let's say over here, this logarithm k would be 0.3, which corresponds to k is 2, and aniline would probably separate here, so those two can be separated, aniline and benzoic acid. Methyl resorcinol, perhaps not. So it appears that not all three of them.
And with the percentage of 10%, the methyl and the aniline could be easily separated at 10%. Or like what
Yes.
happened with those other acids?
Yes, at 10%, those two dots are representing the logarithm k values, and they seem to be nicely separated.
This kind of information can be used for gradient. Like first you can do like 10%.
No, with gradient, it's yes, this type of graphs, yes, but not exactly like this. We will have examples there also.
But if you get this kind of graph, you can have an idea like by using gradients you can like separate them.
I'm afraid not. Yeah, because yeah, gradient can make it more difficult to understand what's going on. Yes, if they are very far away from each other, then we can say, yeah, well, gradient or no gradient, they are separated. But when they are close to each other, then it's difficult to predict what will happen. Okay, but there are already questions about gradient, then let's proceed to gradient elution. Finally, yeah, I understand that you missed the gradient. Okay, so let's see what gradient is and what we can do with it. So, as so far we have just considered the case where the eluent composition doesn't change during the run, then there was no reason to give it a name, this type of elution, but this is called isocratic elution, when the mobile phase composition is not changing during the runtime. In case of gradient elution, mobile phase composition changes during the runtime, so it will become new. And which way? So we can think of this. Usually, everybody knows that in case of reverse phase chromatography, if we use gradient, then the percentage of the organic component increases and the percentage of water phase decreases. Would it be vice versa, so that we reverse it for reverse phase chromatography? Would it make sense? Don't overthink. Just simply. Yes, no? No. Why? I said not to overthink. Thinking is still necessary. Sorry?
I would guess that yes, probably, but somehow it would reverse some.
Well, if we start out with a high percentage of strong element component, what happens? Okay, separation, but what about retention time? Let's take simple case. We start with 100% acetonitrile. No separation, and the retention time is equal to the dead time. So we won't get any separation nor any retention. And that's it. So that's what I meant with don't overthink. So everything is out of the column, and when you decrease the organic percentage, then the compounds are already out of the column. Well, we can flush the column, of course, but there are no compounds anymore. They are already out. Yes, everything will get diluted without separation. Exactly. So yes, that's why we start with the eluent composition, which has weaker eluting power and increase the eluting power over time. This is the way gradient is done. Well, if you think of gas chromatography, over there it's similar. It's pointless to start at high temperature and then decrease the temperature. At high temperature, everything is out of the column, and decreasing the temperature is pointless. Okay, so gradient. Why do we need gradient? If there are many analytes, we need to analyze in one chromatographic run. Then with this isocratic elution, it's maybe not possible to achieve suitable range for K values. Over here, this K value is the range is given even broader, from 0.5 to 20. So we saw that preferably it's between 2 and 10. Here, even wider limits are given, but sometimes we can't achieve even this with just isocratic run. Then sometimes samples contain late eluting matrix components, and after analyzing the analytes in the sample, we need to flush those matrix components out of the column, just for the purpose of cleaning the column. And gradient very easily allows to do this. So at the end of the run, we increase the organic eluent component concentration, and it flushes everything out of the column. Then this third point is usually causing some confusion. It says that gradient elution is suitable for dilute samples which are diluted or dissolved in a weak solvent. So why is the gradient elution now good? Well, if we take a very dilute sample and inject a large volume, in case of isocratic run, then when injecting large volume, then the solvent of the sample itself, this also acts as an eluent, and it carries part of the analyte further. And as it carries the analyte molecules, then it means that the peaks get broad. Now, in case of the situation as described here, we can increase, we can inject the sample in weak solvent mixture, and it will stop, the analyte molecules will stop at the beginning of the column. because the eluting conditions are not favorable for those compounds. They will just be stuck in the column. And somewhat later, only when the eluting power of the eluent is strong enough to elute the compounds, only then they start to move. But by that time, all the sample solution has brought the analyte in the column. It has focused in the beginning of the column and only now starts to move all together. So the peak will not broaden, but we manage to concentrate the analyte molecules in the beginning of the column. So the idea is that with gradient elution, at the starting percent of the eluent composition, the analytes are stationary. They don't move in the column. They all collect to the same spot in the column, and only later, when the eluent strength is high enough, only then they start to move. So analyte pre-concentrates on the column, and we can analyze samples of lower concentration. Okay, and during method development stage, then this gradient elution is a convenient way to get an idea about the components of the sample. With isocratic runs, we could get the same information, but we will probably need 7 injections at different organic percentages, and then we have to monitor when the compounds finally elute from the column. So with less work, we can get more information. Few examples: separation of dialkyl phthalates isocratically. If we try to analyze them at 65% of organic phase, then we see that the latest compound elutes nearly at 20 minutes. Peak is really broad, and still at the same time the compounds 1 to 4 are partially overlapping or more or less overlapping, so we don't get separation in the start of a chromatogram, and at the end the peaks are already too broad. If the organic concentration of the eluent is increased to 80%, then the peaks are narrower for the late eluting compounds, but now the early eluting compounds fully overlap. So there is no way that we can analyze in a reasonable manner both compounds, those which tend to elute late and those which tend to elute early. We should have 2 different runs, or what we can do is to use gradient elution. And with gradient elution, at least it was simulated, we see that the peaks are nicely separated from each other. And furthermore, what is evident from here is that all the peaks have more or less the same width. At some point I mentioned that in case of isocratic elution, the later eluting peaks are broader, as we can see also here. And in gradient elution, all the peaks have the same width. It seems that the latest ones are narrower here. It's just the optical one. I copied it from a book, and I couldn't open the book that much. So it's just an illusion. Okay. Yeah. So I hope that this is sufficient justification why gradient can be a good option. But gradient illusion also has problems. The instrument is more complex. We need gradient mixers, which are quite complex, and sometimes also two pumps are used, which makes it more expensive and complex, of course. Also, optimization of method is more complicated, so there are even more factors to consider. Then some detectors are not compatible with gradient illusion, so again we are limiting ourselves to some certain detectors only. Then column stabilization is needed. In case of isocratic run, in principle, after the last compound has eluted from the column, we can directly inject new sample. But in gradient illusion, we will first have to wait until the initial conditions are equilibrated, and then we can inject it. Now, instruments are different, and those differences pose problems in transferring gradient methods from one instrument to another. And this is quite tricky subject. Also, there is possibility that some salts may precipitate when the solubility of salt in organic modifier is lower, then it's possible that some precipitates occur. But this is perhaps not that common. More problems are caused by additives. For example, if we use some amines or ion pairing reagents in eluent mobile phase, then we have to be even more careful with equilibrating the columns after the gradient illusion. And this may be quite long process. It may seem that, okay, with gradient we can do everything faster, but this equilibration is a long time, which wastes a lot of time. Are there any alternatives available? Indeed, but it depends on what was the reason of using gradient. If the reason was that there are many compounds and we cannot find isocratic conditions, so that for all the compounds K would be in the suitable range, then instead of gradient illusion, we could also use different stationary phase, so cyanocolumn. And we saw that cyanocolumns are much more polar, therefore the retention of non-polar compounds is shorter there. Then tetrahydrofurane can be used instead of acetonitrile or methanol. Well, THF is stronger element, so may help in achieving this K into suitable range. And well, final suggestion using two-dimensional chromatography. Well, two-dimensional chromatography is really a complex thing. So if we don't have a chromatograph which is capable of doing gradient illusion, then probably we don't have also instrumentation for two-dimensional chromatography. But well, at least theoretically, if we cannot separate the compounds in one dimension, then two-dimensional chromatography can be used. All right, now to the method development in gradient illusion. We can use gradient illusion with the aim to develop a gradient method. Or we can use gradient dilution to see what conditions should we use for isocratic method. So both aims are possible and both are very relevant. And the big advantage of gradient dilution is that it separates more peaks in the first run, and there is no danger of overlooking early or late diluting peaks. With isocratic initial runs, we have to do it repeated many times with different organic phase concentrations, but we can do it in one run using gradient. And after this, we can decide whether we have to develop a gradient method or maybe this isocratic method also works. And in principle, we can also find suitable eluent composition for isocratic run. So this can be estimated from the first gradient run. Okay, now eluting power of the eluent increases during the chromatographic run if we speak about gradient elution. So take some time to think of this. So eluting power of the eluent increases. This is what we said in the beginning. We increase the fraction of strong eluent component, meaning that the eluent's eluting power increases. Now, for each compound in the column, the retention factor K decreases during the elution time. Yes? In case of isocratic elution, K remains constant during the elution. In case of gradient elution, K changes. So the retention factor of the compound changes, and while it moves through the column, the K value decreases. So the new eluent composition is stronger. Stronger means that the compound would have shorter retention time. Shorter retention time translates into smaller retention factor. So for each peak, retention factor K decreases during its migration in the column. And those columns which have shorter retention times, those start moving in the column at lower organic percent in the eluent. And of course, those which have longer retention times, they start moving a bit later. And those compounds that elute later in the chromatogram, they initially in the column, they are just stationary. They reach the column, but the eluent is so weak for them that they mostly partition into the stationary phase and they remain there. And until the gradient is, or the eluent composition is suitable for them to continue in mobile phase. Okay, so there is no single K for any compound moving in the column, and in gradient elution, this effective K denoted by this star symbol is used. So effective K is determined, and it's approximately corresponding to the K of the compound when it's in the middle of the column. So it started moving, reached the midpoint of the column, and the K, which this compound experiences at that point, this is the K star, and this is what we try to characterize. And then in case of linear gradient, we mostly speak about linear gradients, and then those K star values are more or less the same for all compounds. And we see this also as we look at the chromatograms, peak widths are the same. So this is because the K values or K star values for all the compounds are the same, roughly. Okay, yes, I wanted to tell those things because they take quite some thinking. So please look at those 2 or 3 last slides that we discussed now. And then next time we will start with this drawing, which is quite messy, I would say. So let's try to understand what's shown in this drawing. Okay, any questions? No questions. Well, yes, gradient dilution is simple, so no questions. Okay, thank you, and then see you next week.